Physics is the one thing we were never supposed to question. From the moment we're old enough to understand why an apple falls instead of floats, we are handed the rules. Speed of light, entropy, gravity, cause and effect. These aren't suggestions. They are the laws that hold reality together. Every planet in its orbit, every atom in its shell, every second ticking forward and never back. All of it governed, controlled, explained. Physics doesn't just describe the universe, it is the universe, or so we thought. Because something strange has been happening in deep space. Not in the imaginations of conspiracy theorists, not in the fever dreams of fringe scientists, in peer-reviewed journals, in NASA mission reports, in data streaming back from the James Webb Space Telescope, humanity's most powerful eye into the cosmos. And what that eye is seeing should not be possible. Objects moving in ways that violate known mechanics. Galaxies that are too old to exist. Energy appearing where there should be nothing. Structures so vast they break the models we use to explain everything else. These are not anomalies that scientists quietly file away. These are published, studied, confirmed. And still, they have no explanation. That's the part that should unsettle you. Because if physics governs the universe, if these laws are truly unbreakable, then what happens when the universe itself refuses to obey them? What does it mean when reality stops following the rule book we wrote to describe it? By the end of this, you will not be able to answer that question. But you will never stop asking it. For most of human history, the night sky was a mystery we could only stare at. Then came the equations. Then came the telescopes. Then came the mathematics that connected everything. The speed at which galaxies move. The age of light arriving from billions of years away. The precise temperature of space itself. One by one, the pieces locked into place. And by the middle of the 20th century, we had something extraordinary. A complete story of how everything began. The Big Bang. 13.8 billion years ago, all of existence, every atom, every force, every dimension of space and time, erupted from a single point smaller than anything we can measure. In the first seconds, the universe was a plasma of pure energy. Then matter formed. Then gravity pulled that matter together. Stars ignited, galaxies assembled, slowly, over hundreds of millions of years. First came the small, chaotic, irregular ones. Then gradually, the large structured spirals. It took time, enormous amounts of time. The universe, according to every model we trusted, needed billions of years to produce what we see today. This wasn't a rough guess, it was tested. It was refined across decades of observation. It predicted things that were later confirmed. The ratio of hydrogen to helium, the faint background radiation left over from the Big Bang itself, the measured expansion rate of the universe. Every test came back positive. Every measurement fit the model. Physicists were not arrogant about this. They were simply confident. The way you are confident the floor will hold you when you step out of bed. It had never failed before. Then the James Webb Space Telescope opened its eye. JWST was launched in December of 2021, designed to see further back in time than any instrument in human history. Light takes time to travel. The further away something is, the older the light reaching us, which means looking deep into space is the same as looking deep into the past. Astronomers pointed the telescope at regions of sky that appeared, to Hubble, to be mostly empty. They expected to find the early universe in its infancy. Small, scattered proto-galaxies, the primitive building blocks of structure, the cosmic equivalent of a construction site still laying its foundation. What they found instead stopped the scientific community in its tracks. Fully formed massive galaxies, ancient, structured. Some of them, containing hundreds of billions of stars, existing just 300 to 500 million years after the Big Bang. When according to every model we had built and trusted and tested, the universe should not have had nearly enough time to produce them. These weren't faint hints. These weren't ambiguous signals requiring creative interpretation. They were unmistakable, real, confirmed across multiple wavelengths by multiple teams in multiple peer-reviewed journals, galaxies that should not have been able to exist yet. And there they were, staring back across 13 billion years of space, completely indifferent to the timeline we had constructed for them. One of the lead researchers on the JWST early galaxy studies described the discovery as finding a fully grown adult standing in a hospital nursery. The analogy is precise. You have no framework for it, and the evidence is sitting right in front of you, impossible to dismiss. Here is why this matters more than it might seem on the surface. The Big Bang model doesn't just tell us how old the universe is. It tells us the rate at which structure forms. It tells us how long gravity needs to pull matter into stars, and how long stars need to live and die before their remnants can coalesce into the next generation. It is a tightly interlocking system. Change one variable and dozens of others no longer hold. The discovery of these ancient massive galaxies isn't a footnote to the standard model. It is a crack running directly through its load-bearing wall. If the universe could produce galaxies that large, that fast, something in our understanding of the early cosmos is fundamentally wrong. And the terrifying part is that we don't yet know what. The leading candidates, accelerated star formation rates, exotic dark matter behavior, new physics governing how matter clumps, are all speculative. None are confirmed. All of them, if true, would require rewriting major chapters of cosmology. Scientists are not panicking, but they are paying close attention in a way they haven't had to for a very long time. Because the data from JWST isn't improving with recalibration. The galaxies are there. The timeline doesn't fit. And the gap between what the model predicted and what the telescope found is not closing. If anything, it is widening. But here's what makes this particular crack even more unsettling. It isn't the only one. Long before JWST began its observations, something was already hiding in the oldest image we have ever captured, the cosmic microwave background radiation. The CMB is the afterglow of the Big Bang itself. It is the faint thermal radiation that permeates the entire observable universe, a snapshot of the cosmos when it was less than 400,000 years old. Every point in the sky contributes a tiny signal. The temperature variations across this image are minute, fluctuations of 100,000th of a degree, and they are supposed to be randomly distributed. Slightly warmer here, slightly cooler there. Statistically uniform, statistically predictable, except for one place. In the southern constellation of Eridanus, there is a region of the CMB so cold, so empty, so anomalously devoid of signal that it defies every statistical model ever applied to it. Not slightly cold, not mildly unusual. Cold in a way that, according to the mathematics of random distribution, should occur less than once across the entire observable universe. It spans roughly 1.8 billion light-years, and inside it, there is almost nothing. No galaxies. A near total absence of the matter that should statistically be present. Scientists call it the cosmic cold spot, and after decades of study, it remains unexplained. Conventional hypotheses were exhausted one by one. A supervoid, a region of space with less matter than average, was identified inside it, but even that void is not large or empty enough to account for the full temperature anomaly. Instrumental error was ruled out. The cold spot appears in independent data from both the WMAP and Planck satellite missions. Statistical chance was calculated and recalculated. It remains by any rigorous measure implausibly extreme. which left scientists with a possibility so strange that most are reluctant to state it plainly, even now. Some cosmologists have proposed that the cold spot is a bruise, a scar left on the fabric of our universe by a collision with another universe. Not metaphorically, literally. A parallel universe existing adjacent to ours within a higher dimensional multiverse, whose physical contact during the period of cosmic inflation left an imprint we are still measuring today. The mathematics of eternal inflation, the same mathematics that naturally produces the Big Bang, also naturally produces an infinite number of bubble universes expanding alongside our own. When those bubbles collide, they leave marks. And the cold spot, in both its scale and its depth, is consistent with exactly that kind of mark. This is not science fiction. The researchers who proposed this hypothesis published it in peer-reviewed journals. It has not been disproven. It has also not been confirmed, because confirming it may lie permanently beyond the reach of any instrument we can build, which means we are left with something harder to live with than a confirmed answer. A genuine scientific possibility, taken seriously by credentialed cosmologists, that we have detected the physical fingerprint of another universe. With no way to know for certain, let that settle for a moment. Two discoveries. One says the universe built itself faster than physics allows. The other says something may have reached in from entirely outside the universe and left a mark we still cannot erase. Neither has a clean resolution. Both are sitting in accepted, published, peer-reviewed data, not as fringe proposals, but as open wounds in the body of cosmology that the best minds on Earth are actively pressing against without finding a way through. You were told that physics is the rulebook. You were told the Big Bang model had been tested and confirmed and trusted. Both of those things remain true. And yet here we are, staring at evidence that the rulebook has missing pages and that something may have been writing in the margins all along. There is one rule in physics that even people who hate physics know. Nothing travels faster than light. Not a rocket, not a signal, not a thought. The speed of light, approximately 299,792 kilometers per second, is the universal speed limit. It isn't a boundary that technology might one day overcome. It is woven into the fundamental structure of space-time itself. Einstein proved it. Every experiment ever conducted has confirmed it. Violate it. And you don't just break a law of physics. You break causality. You break the ability to distinguish cause from effect. You break time itself. This is why physicists treat it as sacred in a way they treat almost nothing else. It is the one line that has never, in over a century of relentless testing, been crossed, which makes what astronomers observed erupting from the cores of certain quasars deeply, uncomfortably strange. Quasars are among the most energetic objects in the known universe, the blazing cores of distant galaxies powered by supermassive black holes consuming matter at an almost incomprehensible rate. As material spirals inward, some of it gets redirected outward in the form of jets. Narrow, focused streams of superheated plasma fired along the black hole's magnetic axis at tremendous velocity. These jets are powerful enough to span thousands of light years. They are among the most dramatic phenomena in the observable cosmos. And when astronomers tracked their motion across the sky over time, they observed something that should have been impossible. The jets appeared to be moving faster than light, not slightly faster, in some cases many times faster. The measurements were not ambiguous, the math was not wrong, and for a brief, disorienting period, physicists had to confront the possibility that something in deep space was violating the single most protected rule in all of science. The explanation when it came was technically reassuring and philosophically unnerving in a different way. The effect is an optical illusion, produced by the geometry of the jet's motion relative to the observer. When a jet is aimed at a nearly perfect angle toward Earth and moving at a significant fraction of the speed of light, the light emitted at successive points along the jet's path arrives at our instruments bunched so closely together that the jet appears to cross more distance in less time than it actually does. The apparent velocity is an artifact of perspective, not a violation of physics. The jets are not actually breaking the light barrier. But here is the part that nobody wants to sit with too long. We did not know that until we worked backward from the assumption that the answer had to fit the rules. We observed what looked like superluminal motion. And then we constructed an explanation to preserve the law we already trusted. The observation came first. The law survived only because the geometry happened to allow it. There is no guarantee the next anomalous observation will offer the same escape route. And the deeper question, how many things in space are we misreading because we interpret data through the lens of what we already believe? That question has no clean answer. Because here is where it gets genuinely disturbing. The quasar jets offered an explanation. What quantum mechanics offers, in the case of entanglement, is not an explanation. It is a confirmation. Quantum entanglement is not a theory. It is not a hypothesis. It is one of the most rigorously tested phenomena in the history of experimental physics. When two particles become entangled, when their quantum states become correlated through interaction, something binds them that has no classical analog. Measure one particle, and the other particle's state is determined instantaneously, not after a brief delay, not after a signal travels between them at the speed of light, instantly, regardless of the distance between them. Einstein despised this. He called it spooky action at a distance, not as a term of endearment, but as a term of rejection. He was convinced the apparent instantaneous connection was an illusion, that the particles must carry hidden information from the moment of their entanglement, predetermining the outcome of any future measurement. He spent years trying to disprove the phenomenon. He failed. Every experiment conducted in the decades since has confirmed what Einstein refused to accept. The correlation is real, it is instantaneous, and it does not diminish with distance. In 2022, the Nobel Prize in Physics was awarded specifically for experiments that closed every remaining loophole in the proof of quantum entanglement. The science is not in dispute. The connection is real. Two particles, separated by any distance, including in principle billions of light years, influence each other's states without any signal passing between them, with no travel time, with no medium, instantaneously. Now hold both things in your mind at the same time. General relativity, Einstein's own theory, proves that nothing travels faster than light. Quantum mechanics, tested and confirmed across thousands of experiments, validated by Nobel committees and particle accelerators and the chips inside quantum computers, proves that entangled particles influence each other with no travel time whatsoever. Both theories are correct. Both are proven. Both are used every day in real-world applications. GPS systems depend on general relativity. Quantum cryptography depends on entanglement. Neither theory is fringe, neither is approximate, and yet they contradict each other at the most fundamental level possible. Physicists are aware of this. They have been aware of it for decades. The standard answer is that entanglement cannot be used to transmit classical information faster than light. You cannot encode a deliberate message in the correlation, only detect the correlation after the fact. This preserves causality in a technical sense, but it does not explain the mechanism. It does not explain how two particles, separated by a distance that light would take billions of years to cross, know about each other's states the instant one of them is measured. There is no known force, No known field, no known particle that carries the connection. It simply exists. It is instantaneous. It operates at cosmic scale. And no one, not one physicist alive, can tell you how. That alone would be enough to leave you unsettled for the rest of the week. But in 1977, something happened that introduced a third and entirely different kind of violation. Not of a physical law, but of every statistical probability we use to describe a silent universe. On August 15th, 1977, astronomer Jerry Amon was reviewing data from the Big Ear Radio Telescope at Ohio State University, a telescope operating as part of a systematic search for extraterrestrial radio signals. Most of what such a telescope receives is noise, thermal static, background radiation, the faint, diffuse whisper of a universe that produces no intentional transmissions. Amon had reviewed thousands of readouts. He expected thousands more. Then he saw something unlike anything the telescope had recorded before or since. For 72 seconds, the telescope received a narrowband radio signal at a frequency remarkably close to 1,420 megahertz, the frequency at which hydrogen, the most abundant element in the universe, naturally emits radiation. This frequency is significant. Scientists working in the search for extraterrestrial intelligence had long identified it as a logical channel for deliberate communication, because any technologically advanced civilization would know about hydrogen and would know that any other civilization listening would know about it too. The signal rose precisely as a radio source outside our solar system would be expected to rise, as Earth's rotation carried the telescope beam toward it. It peaked. It fell. It followed the exact pattern of a distant point source passing through the instrument's field of view. Amon circled the printout in red ink and wrote one word beside the data column. Wow. That single word became the signal's name, and nearly 5 decades later, it remains the strongest candidate for a non-terrestrial radio transmission ever detected. And it has never been heard again. Multiple attempts were made in subsequent years to detect a repeat signal from the same region of sky. All failed. The source, traced to a direction between the constellation Sagittarius and the galactic center, has yielded nothing on any subsequent observation. In 2016, a team proposed that hydrogen clouds associated with nearby comets might explain the signal, a hypothesis that attracted media attention and significant scientific skepticism in equal measure. The comets in question were not confirmed to be in the correct position during the observation window. The signal's narrowband characteristics and intensity profile remain stubbornly difficult to account for through any natural mechanism proposed so far. But what is perhaps most disturbing about the WOW signal is not the signal itself. It is the institutional response, or rather the near absence of one. The reaction from the broader scientific establishment was not urgency. There was no coordinated, sustained campaign to monitor the source region with every available instrument, no redirected funding, no dedicated follow-up mission. For decades, the WOW signal was quietly categorized as an interesting anomaly and largely set aside. The Big Ear telescope itself was demolished in 1998 to make room for a golf course expansion. The data from that night has never been fully explained, and the civilization that received the signal mostly moved on. Why? That is not a rhetorical question. It is a genuine one. If a structured, narrowband radio transmission of precisely the kind scientists designed their search programs to detect was received once from deep space, matching no known natural source, the logical response is to look again, harder, longer, with more instruments and more urgency. The fact that this did not happen, not because of a lack of technical capability, but because of institutional inertia, funding constraints, and a quiet collective reluctance to pursue the implications of a confirmed answer, is itself a data point worth sitting with. three discoveries. A plasma jet that appeared to break the speed of light, explained only by geometry, and our own willingness to preserve the law we trusted. Two particles connected across any distance in the universe by something instantaneous and invisible that contradicts the most tested theory in physics, and 72 seconds of structured signal from deep space that has never been explained, never repeated, and never seriously pursued at the scale the discovery warranted. Motion violated the rules. Information violated the rules. And something in the night sky, on a single August evening nearly half a century ago, may have spoken to us in the exact frequency we designed ourselves to recognize, and we looked away. What comes next is something different altogether. Not objects moving in the wrong way, not signals traveling without time, but entire regions of the universe that appear to exist outside the known laws of physics, as if whole sections of the cosmos never received the rulebook in the first place. There is a principle that sits beneath all of modern cosmology, like a concrete foundation beneath a skyscraper. You rarely hear it discussed outside of academic circles. It doesn't have the cultural fame of the speed of light or the Big Bang. But without it, virtually every model, every simulation, every prediction cosmologists make about the large-scale structure of the universe ceases to function. It is called the cosmological principle, and its claim is simple. At large enough scales, the universe looks the same in every direction. Matter is distributed roughly uniformly. No region of space is fundamentally different from any other. The universe, viewed from far enough away, is smooth. This is not an aesthetic preference. It is a mathematical load-bearing wall. The equations that describe how the universe expands, how dark matter clusters, how galaxies form and migrate and collide, all of it is built on the assumption that the cosmological principle holds. Remove it, and you don't just lose one model. You lose the scaffolding that holds the entire discipline together. Which is precisely why what astronomers have found in the large-scale structure of the universe over the past several decades is not merely surprising. It is, in the most literal scientific sense, a crisis. Because the universe is not smooth. It is not roughly uniform. It is not homogeneous at the scales the cosmological principle requires. What it actually contains, what the data actually shows, are structures so enormous, so coherent, so completely impossible under any conventional model of cosmic evolution that the astronomers who discovered them spent years checking their instruments before publishing. Not because they doubted their data, because they doubted anyone would believe it. To understand why these structures are impossible, you first need to understand what the universe had to work with and how little time it has had to work with it. After the Big Bang, the universe began as an almost perfectly uniform hot plasma. The key word is almost. There were tiny fluctuations in density, regions that were fractionally, imperceptibly denser than their surroundings. Gravity amplified those fluctuations over time. Denser regions pulled in more matter. Matter collected into filaments. Filaments intersected at nodes where galaxy clusters formed. The result over billions of years is what astronomers call the cosmic web. An intricate foam-like structure of filaments and voids that spans the observable universe. This process has a speed limit. The speed at which matter can clump under gravity, the rate at which large-scale structure can grow, is constrained. Physicists have calculated it precisely. They know how large a coherent structure can become given the age of the universe and the rate at which matter moves. The upper boundary, the point at which structures become too large to have formed through any gravitational process consistent with the Big Bang timeline, sits at roughly 1.2 billion light-years. That is the size beyond which, according to every standard model we possess, coherent structures should not exist. The Hercules Corona Borealis Great Wall is 10 billion light-years across. Let that number exist in your mind for a moment before moving on. 10 billion. The observable universe itself is roughly 93 billion light-years in diameter. The structure we are discussing spans more than 1/10 of everything we can see. It was identified through the distribution of gamma-ray bursts, the most energetic explosions in the known universe, which cluster in that region of space, with a concentration so statistically improbable that the clustering itself demanded an explanation. The explanation was the structure, a superstructure, a filament or wall of matter and galaxy clusters so vast that it defies every time constraint our models impose on the formation of large-scale cosmic architecture. For the universe to have built something 10 billion light-years across, using only gravity and the matter available after the Big Bang, it would have needed significantly more time than it has had. The math doesn't bend to accommodate it. There is no parameter you can adjust within the standard model that produces an object this large within the universe's current age. And yet the gamma-ray burst data is not ambiguous. The structure is there. It is real. And the community of cosmologists who study it has not produced a consensus explanation for how it exists. The leading responses fall into three uncomfortable categories. The first is that the structure is somehow a statistical artifact, that the gamma-ray burst distribution that revealed it is misleading, and that closer analysis will dissolve it into noise. This explanation is increasingly difficult to maintain as the data accumulates. The second is that the standard model is missing something, that there is a mechanism of structure formation we have not yet identified, operating faster or at larger scales than current physics allows. The third is the one most rarely stated in public, that the universe is older than we think, or that the Big Bang was not the beginning we assumed it was, and that the timeline into which we have placed all of cosmic history requires revision at the most fundamental level. None of these are comfortable positions. All of them are being quietly discussed. And before the field had time to reach any consensus on the Great Wall, a new discovery arrived to deepen the wound. In 2021, astronomer Alexia Lopez, working with data from hundreds of thousands of galaxies mapped in the Sloan Digital Sky Survey, identified a curved structure 3.3 billion light-years long, sweeping across the sky in the shape of a vast arc, consistent in its curvature, statistically coherent, and entirely unexplained. She called it the Giant Arc, and unlike the Hercules Corona Borealis Great Wall, which some researchers still debate, the Giant Arc arrived with rigorous statistical analysis attached. Analysis showing that the probability of this structure arising by chance, in a universe that actually obeys the cosmological principle, is approximately 1 in 50,000. 1 in 50,000. To put that number in perspective, a 1 in 50,000 probability is not a curiosity. It is not a footnote. In any other field of empirical inquiry, a result that improbable would trigger an immediate and widespread investigation into the assumption being violated. In medicine, a result with those odds would halt trials. In engineering, it would ground fleets. In cosmology, the Giant Arc was met with something closer to cautious acknowledgement, a recognition that it was significant, followed by an institutional hesitation that remains difficult to explain. Because the Giant Arc does not merely challenge our models of how the universe is structured, it challenges the cosmological principle directly. If a coherent, curved structure 3.3 billion light-years long exists, if the universe contains at those scales organized geometry rather than smooth uniformity, then the foundational assumption that underlies all of modern cosmological modeling is wrong, not slightly inaccurate, not in need of minor correction, structurally, fundamentally wrong. The cosmological principle is not a trivial assumption that cosmologists made carelessly and can revise without consequence. It is embedded in the field equations. It is embedded in how we calculate the expansion rate of the universe. It is embedded in how we infer the amount of dark matter and dark energy required to produce the universe we observe. Remove it, and the ripple effects cascade through virtually every major result in cosmology produced over the last century. The models that produced those results were built on a foundation that the giant arc suggests is cracked. And if the foundation is cracked, the question of how much of the structure above it remains valid is genuinely open. This is the part that the coverage of these discoveries rarely emphasizes. When the giant arc was reported in popular science media, the framing was typically one of wonder. Look how big the universe is. Look at what we're still finding. The framing was not. This discovery invalidates a core assumption of the mathematical framework we use to model everything. But that is the accurate framing? That is what the numbers actually say. And the numbers say something else too. Something that emerges when you place the giant arc and the Hercules Corona Borealis Great Wall alongside each other and look at what they have in common. Both exceed, by enormous margins, the theoretical maximum size for coherent structures in a universe of the age and composition we have measured. Both require, if they formed through gravitational processes, either a timeline far longer than the Big Bang allows or a mechanism of structure formation that does not exist in any current model. Both were found not by exotic new instruments probing the frontier of detectability, but by careful, methodical analysis of existing survey data, which means the possibility exists that more structures like them are hiding in the datasets we already have, waiting for someone to look in the right way. This is the detail that should produce in you something more than wonder, because wonder is a comfortable emotion. What the data actually warrants is something closer to vertigo, the specific sensation of reaching for a wall you assumed was solid and finding your hand passing through it. We built the entire architecture of modern cosmology on the assumption that the universe, at large enough scales, is uniform. That assumption was not arbitrary. It was mathematically convenient, it was philosophically elegant, and for a long time, it appeared to be confirmed by observation. But the universe was never asked whether it agreed. And the universe, it turns out, has a different opinion. It built structures that the cosmological principle says it could not. It arranged matter in curved, coherent geometries that the principle says should dissolve into uniformity. It filled 10 billion light-years with something organized and enormous and ancient in ways that the timeline of the Big Bang cannot account for. Either the universe is older than we know, or it formed faster than physics allows, or it operates by mechanisms we have not yet discovered. Those three options are not equally disturbing. They are all maximally disturbing in different directions, and we do not currently know which one is true, or whether the answer is some combination of all three. What we do know is this: the largest structures in the observable universe are telling us, in the clearest observational language available to science, that something about our model of the universe is deeply, fundamentally wrong. Not at the margins, at the center. Not in a way that future instruments might clarify with a minor adjustment. In a way that may require tearing down and rebuilding the framework we use to understand what the universe is, how old it is, and how it became what we see. The structures exist. The math says they shouldn't. And the gap between those two facts is not closing. If that thought sits uneasily in you, if there is something in the back of your mind that wants the rules to hold, that wants physics to reassert itself and produce an explanation that makes the discomfort go away, hold on to that feeling. Because what comes next does not offer reassurance. What comes next involves the objects we thought we understood best. The darkest, most studied, most theorized phenomena in the universe, behaving in ways that break their own definition. Black holes. The one thing in physics that was supposed to be simple. The one rule that was supposed to be absolute. and the one place where the universe apparently decided to break even that. Stephen Hawking was not a man who made mistakes lightly. Over the course of a career spanning 5 decades, he reshaped our understanding of the universe more profoundly than almost any physicist of the 20th century. He proved that black holes have a temperature. He proved that the Big Bang emerged from a singularity. He proved that the laws of thermodynamics apply at the edge of the most extreme objects in the cosmos. He was meticulous, rigorous, and almost pathologically precise. When Stephen Hawking said something was mathematically true, the scientific community listened, which is why the problem he spent the last 40 years of his life unable to solve should terrify you far more than it does. Because Hawking didn't just discover one truth about black holes, he discovered 2. And they cannot both be right. And they are. To understand why this is a crisis, rather than simply a puzzle, you need to understand what a black hole actually is, not the dramatic popular version, but the physical one. A black hole is a region of space-time where gravity has become so extreme that nothing, no matter, no radiation, no information of any kind, can escape once it crosses the boundary called the event horizon. This is not a limitation of technology. It is a geometric property of space-time itself. Inside the event horizon, every possible path through space and time points toward the singularity at the center. There is no trajectory that leads out. The boundary is absolute. The escape velocity exceeds the speed of light. And since nothing travels faster than light, nothing leaves. This was the established picture. Clean, total, absolute. Then, in 1974, Hawking did something that changed everything, and simultaneously broke everything. Using a synthesis of quantum mechanics and general relativity, he demonstrated that black holes are not perfectly black. They emit radiation. At the event horizon, quantum fluctuations cause pairs of particles to spontaneously appear. One particle falling inward, one escaping outward. The escaping particle carries energy away from the black hole. Over immense timescales, this process causes the black hole to lose mass, slowly, imperceptibly, until, in principle, it evaporates completely and ceases to exist. The radiation it emits in this process carries no information about what fell in. It is thermal. It is random. It is, in the language of physics, perfectly scrambled. Hawking radiation was one of the most elegant theoretical discoveries of the 20th century, and it contained, hidden inside it, a catastrophe. Because quantum mechanics, the other great pillar of modern physics, is built on a principle called unitarity. Unitarity states that information is never destroyed, ever. The specific quantum state of any physical system, the precise configuration of every particle, every spin, every energy level, is always conserved. It may be scrambled beyond any practical ability to recover, but it is never erased. The past is always, in principle, recoverable from the present. This is not a minor technical stipulation. It is a foundational requirement of quantum mechanics, tested and confirmed across every experiment the theory has ever been applied to. Remove unitarity and quantum mechanics, the framework that underlies all of chemistry, all of material science, all of modern electronics, breaks down. Now hold both things simultaneously. General relativity says that information falling into a black hole cannot escape. Hawking radiation says that black holes evaporate completely, leaving behind only thermal noise. Quantum mechanics says information cannot be destroyed. If a black hole evaporates and its radiation carries no record of what fell in, then the information that crossed the event horizon is gone. Permanently. Irrecoverably. Which means quantum mechanics is violated. Which means unitarity fails. which means one of the two most successful theories in the history of physics, is fundamentally wrong. This is the black hole information paradox. Hawking himself proposed it. Hawking himself could not resolve it. In 2004, he publicly conceded that information was probably preserved, that he had been wrong to suggest it was destroyed. But his concession came with no mechanism, no proof, and no explanation for where or how the information survives. He simply concluded that it must, because the alternative was too destructive to accept. The paradox has remained open for 50 years. It has attracted more serious theoretical attention than almost any other problem in physics. It has generated competing frameworks: black hole complementarity, the holographic principle, the firewall paradox, island formula calculations, each offering a partial resolution and each introducing new contradictions in the process. The world's most brilliant physicists have bent themselves around this problem for half a century. No consensus exists, no solution has been proven. The wound is still open, and in 2023 it became observable. For nearly 50 years, Hawking radiation existed only as a theoretical prediction. No instrument we possessed was sensitive enough to detect it from an actual astrophysical black hole. The radiation is extraordinarily faint, swamped by every other signal in the cosmos. But in 2023, a team of physicists used an analog system, a carefully engineered flow of ultra-cold atoms designed to mimic the physics of an event horizon, to produce and measure the first experimental signatures consistent with Hawking radiation. The result was not a direct observation of a black hole emitting radiation, but it was a confirmation that the physical mechanism Hawking described is real, is reproducible, and produces exactly the thermal, information-free output that the theory predicts. This sounds like progress, and in one sense it is. But in the sense that matters most, it is not progress at all. It is confirmation that the crisis is real. Because every experimental signature that validates Hawking radiation tightens the information paradox rather than loosening it. Each piece of evidence that the radiation is genuinely thermal, genuinely devoid of information about what fell in, makes the violation of unitarity more concrete, not less. The paradox is no longer a thought experiment. It is an active, measurable, experimentally supported crisis in the foundations of physics, and no one has resolved it. What makes this particularly vertiginous is the question it implies about the nature of reality itself. Unitarity is not just a mathematical convenience. It is the reason the past exists in any meaningful physical sense. If information can be destroyed, if a black hole can consume the precise quantum state of a particle and return nothing but featureless heat, then the universe is not, at its deepest level, deterministic in the way physics has always assumed. The past does not fully determine the future. The future does not fully encode the past. Causality itself becomes something looser, something less absolute than everything we have built our understanding of physical reality upon. Hawking understood this. It is why the problem consumed him. Not because it was intellectually interesting, though it was, but because the stakes of getting it wrong were total. This was not a question about one exotic object in a distant part of the universe. It was a question about whether the laws that govern all information, all matter, all physical processes everywhere are actually consistent with each other. The answer, 50 years on, is we don't know. And the experimental evidence is now confirming that the question is as sharp and as real as Hawking feared. But the information paradox is not the only way black holes are breaking their own definitions, because there is a black hole in the observable universe that is not just challenging our models of physics. It is challenging our models of how galaxies and everything inside them are allowed to exist. TON 618 is a quasar located approximately 10.4 billion light-years from Earth. At its center sits a black hole with a mass of 66 billion times that of our Sun. Not millions, not billions in the range of 5 or 10. 66 billion solar masses compressed into a region of space bounded by an event horizon roughly 2,000 times the diameter of our entire solar system. It is the most massive black hole currently confirmed by direct observational measurement. And its existence is, in a quiet but fundamental way, extremely difficult to explain. The problem is not simply scale. The problem is what that scale implies about the region of space surrounding it. A black hole of this mass exerts gravitational influence across a region so vast that the galaxies within it, the stars, the gas clouds, the entire structure of cosmic real estate in its vicinity, cannot evolve independently of it. Its gravitational sphere of influence swallows and shapes everything nearby. This is not unusual for supermassive black holes. All large galaxies appear to host them, and their masses correlate with the properties of their host galaxies in ways that suggest they co-evolved. But TON 618 is not merely a large supermassive black hole. It is so far beyond the upper end of the expected mass range that the models we use to describe how black holes grow, through accretion, through mergers, through the collapse of massive stars, struggle to account for it. Growing a black hole to 66 billion solar masses requires time, enormous amounts of time. It requires matter, fed consistently into the black hole across billions of years. It requires a sequence of mergers and accretion events that, under our current understanding of black hole growth rates, would push against the limits of what the universe's age permits. TON 618 sits at a redshift that places it deep in the early universe, a universe that, at the time its light was emitted, was only a few billion years old. The question of how something that massive assembled itself that quickly runs directly parallel to the question raised by JWST's ancient galaxies. The timeline does not comfortably accommodate what we observe, and no current model resolves the discrepancy with confidence. There is one more detail about TON 618 that tends not to make it into the popular coverage. The luminosity of this object, the total energy output of the quasar it powers, is so extreme that for a period, it outshone the entire combined light of the Milky Way galaxy by a factor of roughly 140 trillion. One object, one point in space, releasing more energy per unit time than 140 trillion of our suns. The physics of accretion, the physics of radiation pressure, the physics of how much energy a black hole can emit without blowing away its own fuel supply, all of these are stressed at TON 618's luminosity to limits that the models handle only barely. It exists at the absolute edge of what the equations permit, perhaps beyond it. Two violations, then, sitting inside the same category of object. The first, a paradox 50 years old and now experimentally confirmed as real. Information entering a black hole may be destroyed, which means one of the two greatest theories in physics is broken, and we cannot determine which one. The second, a black hole so massive it should not have been able to assemble itself in the time available, sitting at the center of a cosmos that keeps producing things it should not have had time to build. Black holes were supposed to be the ultimate expression of physical law pushed to its extreme. The singularity at their center was described as the point where physics breaks down, where the equations collapse, where the rulebook reaches its final page. But what the last several decades of observation and theory have revealed is something more unsettling than physics breaking down at a singularity. Physics is breaking down here, in the observable universe, in the measurable data, in the equations we use to describe objects we can see and study. The rulebook isn't ending at the singularity. It is unraveling on the way there, and no one, not Hawking, not the Nobel Committee, not the most powerful telescopes we have ever built, has yet found the thread that holds it together. There is something the human mind does that no other known cognitive system does quite the same way. It finds patterns, not just when patterns are there, but relentlessly, automatically, even when they are not. Faces in clouds, meaning in coincidence, cause behind randomness. Neuroscientists call it apophenia. The tendency to perceive connections between unrelated things. It is considered a cognitive bias, a quirk of a brain that evolved to find predators in shadows and therefore errs towards seeing shapes that aren't there. When the pattern detection fires without justification, we call it superstition. We call it paranoia. We tell ourselves that the rational mind corrects for it, steps back, and sees the randomness for what it is. But what happens when the pattern is actually there? What happens when you step back, apply every statistical tool available, run the numbers with cold precision, and the pattern gets stronger, not weaker? What happens when the thing your rational mind was supposed to dismiss turns out to be sitting in the peer-reviewed data, confirmed across independent instruments, present at the largest scale the universe offers for inspection? That is not apophenia. That is discovery. And what has been discovered, quietly, uncomfortably, over the past several decades, is that the universe appears to have been arranged. Not approximately arranged, not loosely structured. Arranged with a precision so extreme, across so many independent variables, that the probability of it being the product of random chance approaches a number so small, it loses all practical meaning. Begin with the constants. Physics runs on numbers. Not arbitrary numbers, specific, fixed values that determine how every force in the universe behaves, how particles interact, how matter and energy relate to each other. The gravitational constant determines how strongly mass attracts mass. The speed of light determines the maximum rate of information transfer. The mass of the electron determines the structure of every atom in existence. The cosmological constant, the energy density of empty space, determines whether the universe expands, contracts, or remains stable. These values are measured. They do not change. And they are, without exception, tuned to values that permit the existence of matter, structure, chemistry, and life with a precision that has no physical explanation. Consider what happens when you adjust them. Increase the gravitational constant by a small fraction, and stars burn out in thousands of years rather than billions. Too fast for planets to form. Too fast for chemistry to reach complexity. Decrease it, and stars never ignite at all. The universe remains a cold, diffuse gas cloud forever. Change the mass of the electron by a few %, and atoms cannot form stable bonds. Chemistry as we know it ceases to exist. Alter the cosmological constant by even a tiny fraction, and this is the one that should stop you. And the universe either collapses back on itself almost immediately or expands so rapidly that matter never clumps into anything. The window of values that permits a universe with structure, with stars, with planets, with any complexity whatsoever is extraordinarily, almost inconceivably narrow. Physicists call this the fine-tuning problem, and it is called a problem not because the universe is finely tuned, that much is simply observation, but because physics has no mechanism that produces fine-tuning. The constants are not derived from deeper principles. They are not predicted by any equation. They are simply measured, found to be what they are, and inserted into the models that describe everything else. There is no known physical reason why the gravitational constant has the value it has, rather than a value 10 times larger or 10 times smaller. It is simply what it is. And what it is happens to sit, with extraordinary precision, inside the narrow corridor that permits the universe we inhabit. The standard scientific response to this observation is the multiverse. The proposal that an enormous or infinite number of universes exist, each with different values of the physical constants, and that we find ourselves in one that permits our existence simply because those are the only universes in which observers can arise. This is a logically coherent response. It is also, at present, entirely untestable. There is no observation we can currently make that would confirm or refute the multiverse hypothesis, which means it functions less as a scientific explanation and more as a philosophical pressure valve, a way of preserving the idea of randomness in the face of data that does not look random. And then there is the axis of evil. The cosmic microwave background, the afterglow of the Big Bang, the oldest light in the universe, was mapped with extraordinary precision by the WMAP satellite beginning in 2001, and later by the Planck mission. The resulting image is one of the most analyzed datasets in scientific history, and buried inside it, confirmed independently by two separate space missions using different instruments and different methodologies, is an anomaly that has no explanation within the standard cosmological model. The largest scale temperature variations in the CMB are not randomly oriented. They are aligned, not roughly aligned, not approximately aligned in a way that might be dismissed as borderline, aligned along a single preferred axis that stretches across the entire observable universe, an axis that, in a genuinely random universe produced by an isotropic Big Bang, has an estimated probability of occurring by chance of less than 1%. The alignment is present in the quadrupole and octupole moments of the CMB, the broadest, largest-scale features of the map, and it persists across datasets, across instruments, across analytical methods. Cosmologists who encountered it named it with a candor that is unusual for academic literature. They called it the axis of evil. Because in a universe governed by the cosmological principle, the principle that no direction is preferred, that the universe has no special orientation, an axis of this kind should not exist. It exists. And here is the detail that tends to be omitted from the general coverage of this anomaly, the detail that moves it from interesting to genuinely unnerving. The axis of evil is not aligned with some arbitrary reference frame. It is aligned with remarkable precision with the plane of Earth's orbit around the Sun, the ecliptic, and with the equinoxes. Cosmologists noticed this alignment early and worked intensively to explain it as an artifact, a product of foreground contamination from our own solar system, a systematic error in the data processing, a bias introduced by our vantage point within the Milky Way. 20 years of analysis later, none of these explanations have fully accounted for the alignment. It remains. After subtracting every known source of local contamination, the axis persists. The implications of this, if taken at face value, are ones that mainstream cosmology is extremely reluctant to articulate. A universe with a preferred axis, an axis aligned with our position in it, is a universe in which our location is not arbitrary. It is a universe in which the structure of space itself, at the largest scales we can observe, bears some relationship to where we are. This is not a conclusion that fits comfortably into any version of the cosmological principle. It is not a conclusion that fits comfortably into any current physical model. And it is a conclusion that, if pursued to its logical end, raises a question so far outside the boundary of conventional scientific discourse that most researchers prefer to search for instrumental error rather than confront it directly. But the error has not been found, and the axis has not dissolved. Place this alongside the fine-tuning of the constants. Place both of them alongside the Hercules Corona Borealis Great Wall, too large to have formed in the available time. Place those alongside the ancient JWST galaxies, assembled faster than the Big Bang allows. Place all of it alongside the cosmic cold spot, a wound in the CMB possibly left by a collision with another universe, and stand back. What you see when you stand far enough back is not a collection of independent anomalies. What you see is a universe that consistently, repeatedly, across wildly different scales and wildly different physical domains, produces results that are improbable in a purely random cosmos. Results that cluster around the same uncomfortable implication, that the universe is not the product of blind, undirected chance operating within fixed and arbitrary constants, that something, some principle, some structure, some condition that we do not yet have the language or the mathematics to describe, shaped it. This is not a religious claim. It is not a spiritual one. It is a statistical and observational one. The data does not tell us what shaped the universe. It does not tell us whether that shaping was the result of a deeper physical law, or a selection effect across a multiverse, or something that has no analog in any framework we currently possess. What the data tells us, what the fine-tuning and the axis of evil and the anomalous structures all tell us collectively and individually, is that the universe as observed is not consistent with pure randomness. The pattern is there. It is in the numbers. It survived every attempt to explain it away, and it is pointed with a precision that should be impossible in a direction that includes us. A random universe does not fine-tune itself to allow consciousness. A random universe does not align its deepest large-scale features with the plane of a single planet's orbit. A random universe does not build structures too large to have formed randomly, or produce galaxies too early for its own timeline, or leave cold scars in its oldest light that trace the exact dimensions of a collision with something else entirely. These things do not happen in random systems. They happen in systems that have been shaped. Officially, this is all coincidence. Officially, there are explanations, partial, contested, unconfirmed, for each anomaly in isolation. Officially, the multiverse accounts for the fine-tuning, local contamination accounts for the axis, and large-scale structure models will eventually catch up to the observations. Officially, physics is not broken. The rulebook is intact, but the data is accumulating. And the data is speaking in a direction that the official position is working very hard not to hear. Because if the pattern is real, if the universe is not random, then the question that follows is one that no equation in physics is designed to answer. And that question is the one you have been approaching, one discovery at a time, since the first moment of this video. What made it not random? And why does the pattern include you? Before this video ends, there is one more discovery. It is not located in a distant galaxy. It was not captured by JWST or detected by a radio telescope in Ohio, or calculated from the temperature fluctuations of the CMB. It cannot be measured in light years or solar masses or giga-electron volts. But it is, by any honest mathematical accounting, the most improbable thing we have encountered in this entire video. More improbable than a galaxy 10 billion light-years wide. More improbable than particles connected across the universe with no travel time. More improbable than a signal from deep space that matched no natural source and was never heard again. The most improbable discovery in the known universe is you. Not you as a metaphor. Not you as a philosophical concept. You, specifically, physically, biologically, as a chain of causally linked events stretching back 13.8 billion years, every link of which had to hold, every branch of which had to fall the right way. For a conscious mind to be sitting where you are sitting right now watching this, start at the beginning. The Big Bang produced hydrogen and helium and almost nothing else. The heavier elements, carbon, oxygen, nitrogen, iron, calcium, do not emerge from a Big Bang. They are forged inside stars in the nuclear furnaces at their cores over billions of years of sustained fusion. When a massive star exhausts its fuel and collapses, it detonates in a supernova, an explosion violent enough to scatter those elements across light years of space. The carbon in your body was not here at the beginning. It was cooked inside a star that lived and died before our sun existed. A specific star, in a specific location, at a specific time. One whose explosion seeded the molecular cloud that would eventually collapse, under the right conditions of pressure and temperature, disturbed perhaps by the shock wave of yet another nearby supernova, into our solar system. The probability of that collapse producing a star with the right mass to sustain stable fusion for billions of years, orbited by a rocky planet at precisely the right distance to maintain liquid water, is not high. The probability of that planet retaining its liquid water, not losing its atmosphere to solar wind the way Mars did, not being sterilized by its star's radiation, not being struck by an impactor large enough to strip its surface, over the 4.5 billion years required for life to emerge from chemistry, is lower still. The probability of the specific asteroid impact 66 million years ago that ended the reign of the dinosaurs and cleared the ecological space for small mammals to diversify and eventually produce primates. An impact that required an object of the right size, traveling at the right angle, arriving at the right moment in evolutionary history, sits at a value that, calculated honestly, approaches the limit of what numbers can usefully express. And we have not yet arrived at you. Every human alive today is the product of an unbroken chain of ancestors stretching back to the first replicating molecules in the early ocean. Every single one of those ancestors, across billions of years, through 5 mass extinction events, through ice ages and volcanic winters and the random violence of a biosphere that was never designed to be kind, survived long enough to reproduce. Not almost survived. Survived. Every link held. The chain never broke. Any single ancestor at any single point in that chain failing to reach reproductive age would have erased every descendant that would ever follow. You are not the product of a fortunate lineage. You are the product of an unbroken sequence of fortunate outcomes so long that the human mind cannot hold its full length without collapsing into the nearest available seat. The physicist and author calculate these probabilities differently, arriving at different numbers through different methodologies. But they converge on the same conclusion: the specific you. Not a human, not a primate, not a conscious being, but you with your particular genome, your particular moment of birth, your particular configuration of matter and memory, is a statistical event so improbable that a universe generating random outcomes for the entirety of its 13.8 billion year lifespan should not have produced it. The number is not merely small, it is, for practical purposes, indistinguishable from zero. And yet here you are. Now go back through everything this video has shown you, not as a list of anomalies, as a sequence, as a chain. The Big Bang had to produce the precise values of the physical constants: the gravitational constant, the cosmological constant, the electron mass, within the extraordinarily narrow range that permits atoms, chemistry, and stars. If any of those constants had been fractionally different, there would be no matter, no stars, no elements heavier than helium, no you. The galaxies JWST found, assembled impossibly fast in the early universe, had to form when they did, seeding the cosmic web with the density fluctuations that would eventually pull a molecular cloud together in the right corner of the Milky Way, the cold spot in the CMB, possibly a scar from a collision with another universe, had to be a scar and not a wound. The collision, if it happened, had to leave a mark without unraveling the physics on this side of the boundary. The quasar jets, the entangled particles, the wow signal. Each of these exists in a universe that somehow maintained its internal consistency long enough for stars to form, for planets to stabilize, for chemistry to reach complexity. The structures that should not exist, the Great Wall, the giant arc, formed in a universe that nonetheless maintained the conditions for smaller-scale structure, for solar systems, for liquid water. TON 618, whose gravitational influence reshapes everything around it, sits billions of light-years from here, far enough that its influence never reached this corner of the cosmos with enough force to disrupt what was quietly assembling. The information paradox, whatever its resolution, did not, in the vicinity of this planet, erase the quantum states that underlie the molecular machinery of life. Everything that should have gone wrong didn't. Not here, not in the sequence that led to you. This is either the most extraordinary coincidence in the history of the universe, or it is something else. And physics, with all of its precision, all of its instruments, all of its Nobel Prizes and peer-reviewed journals and space telescopes, does not currently have a framework that distinguishes between those two possibilities. Most people move through their lives without encountering this thought directly. Not because the thought is new, philosophers and physicists have circled it for decades, but because the weight of it, when you hold it fully, is not comfortable. It is not the warm, greeting card version of "you are special." It is something colder and stranger, and more destabilizing than that. It is the recognition that the chain of improbabilities required to produce a conscious mind in a universe that appears to be governed by fixed physical laws is so long and so precise that the laws themselves struggle to account for it. You are made of carbon forged in a dead star. You are the product of a planetary history that required 5 extinctions to clear the path. You exist in a universe whose constants were set by some mechanism entirely unknown to physics, to values that permit your existence. You are watching a video about the impossibility of things that shouldn't exist, and you are the most impossible thing in it. The universe broke 10 rules to produce what you are looking at right now from the inside. The galaxies that formed too early. The structures too large for the timeline. The constants too precise for randomness. The signal from deep space that matched the frequency we designed to recognize. The axis that shouldn't be there, pointing in a direction that includes us. Taken separately, each of these is an anomaly. Taken together, as the context within which your existence became possible, they are something else. They are the conditions. The specific, improbable, unrepeated conditions that a universe somehow managed to produce once, in a way that eventually resulted in a mind capable of looking back and asking why. You were told at the beginning of this video that physics is the rulebook of the universe. You have now seen 10 places where that rulebook appears to be wrong, incomplete, or simply inadequate to describe what the universe has actually done. Ancient galaxies, impossible structures, faster-than-light appearances, instantaneous connections across cosmic distances, a structured signal from deep space, a fine-tuned reality, a preferred axis in the oldest light we can see, a paradox at the heart of the darkest objects in existence, and a chain of causation so improbable that every mathematician who has tried to calculate it has arrived at a number that cannot be meaningfully distinguished from impossible. And at the end of all of it, here you are, conscious, aware, asking the question. Inside the universe that produced the question, made of the matter that shouldn't have assembled, on the planet that shouldn't have survived, descended from the chain that never broke, in the cosmos that broke its own rules to get here. Physics says you shouldn't exist, but you do. And maybe, after everything, that is the only discovery that actually matters.